Welcome folks, a video today on the determinant of a matrix. In this video we'll start a little bit aside and talk about a special class of matrices called elementary matrices. Then we'll construct the definition of the determinant of a matrix and see how to compute a few determinants. So first, elementary matrices. We'll motivate this discussion of elementary matrices by having a look at the result of a few different matrices times this given matrix A. So here I've cooked up a matrix E sub 1, 3 that ends up being an elementary matrix. What we see after multiplying by the matrix A is that the matrix we get multiplying E1, 3 by A appears to have a particular row operation. It appears that our new matrix is the matrix A with row 1 and row 3 swapped. Let's look at another one. Here's another one. I'm calling this matrix E sub 2, 2. So you can see it's a matrix with a 2 in the second row. And we see what happens that when we multiply A by the matrix E sub 2, 2 is that it appears the new matrix is the matrix A where we've multiplied the second row by 2. Okay, so again here we see that we can accomplish the row operation of multiplying the second row by 2, multiplying by this matrix E sub 2, 2. Not surprisingly, there's a third matrix. This third matrix is called E sub 3, 1, 2. It has a 2 in the third element of the first row. And we see that when we multiply A by E sub 3, 1, 2, that it has the effect of multiplying row 3 by 2, adding it to row 1, creating a new row 1, and leaving row 3 alone. So this is a familiar row operation too. Okay, it turns out that row operations can always be accomplished by matrix multiplication. We call the matrices that accomplish such row operations elementary matrices. So here are those three elementary matrices, and I give you a chance to play with these a little bit in the worksheet. There's a bit of an index alphabet soup here, but there's a matrix E sub I, J that accomplishes the task of swapping row I and row J. There's a matrix E sub I alpha that accomplishes the task of multiplying row I by the constant alpha. And there's a matrix E sub I j alpha that has the effect of multiplying row I by the constant alpha, adding it to row J, giving us a new row J, and leaving row I alone. Okay, so again, an opportunity for you to play with those a little bit on the worksheet. Okay, so the theorem is that that these matrices always work, and the proof is sort of beyond the scope of this class, but it just uses that alphabet soup from these elementary matrices in order to show that the outcome of this matrix multiplication is in fact the desired row operation. Okay, the important outcome of this definition of three different elementary matrices is that every elementary matrix is non-singular. Now, again, the proof is a little bit beyond the scope of our class here too, but the idea here is that that since every elementary row operation is reversible, that multiplying by that reversible row operation gives us effectively the identity matrix. So for the first set of elementary row operations, that is swapping row I and row J, we can show that E sub ij times E sub ij gives us back the identity. Of course, the identity is non-singular, therefore E sub ij must be non-singular. It works similarly for multiplying a row by a constant. Okay, if I go through and multiply row I by a constant, and then I multiply row I by 1 over that constant, I get back the identity matrix. And there's a reversible operation for the action of multiplying row I by the constant alpha, adding it to row j, creating a new row j, and leaving row I alone as well. Here's what that is. Okay, it turns out if I then go ahead and multiply row I by the constant minus alpha, adding it to row j, creating a new row j, and leaving row I alone, I get back what I started with. So in all three cases here, the identity is non-singular, therefore the product of the two matrices is non-singular, showing that each matrix is singular. So it's a little bit of an alphabet soup to do this, and I'm not going to require that you know that proof, but the point is that every elementary matrix is non-singular. This is important because it turns out then that we can show every non-singular matrix is a product of elementary matrices. Okay, that's what this theorem says. If A is non-singular, then there are elementary matrices E sub 1, E sub 2, out to E sub t, that A is a product of those T elementary matrices. So the proof of this is pretty cool, and it relies on the fact that when A is non-singular, A can be reduced to the identity. Okay, in other words, there's a finite sequence, say, of T moves, T row operations, such that A reduces to the identity. Well, now we know that each of these row operations can be accomplished through matrix multiplication by one of these elementary matrices. Okay, so I'm going to call the row operations that get us to the identity matrix E1 prime, E2 prime, out to ET prime. Now, of course, each of these row operations is reversible, and we'll just say that the reversible row operation is for E1 prime is just E1, for E2 prime is E2, and so on and so forth. So we can reverse the first operation multiplying on the left by E1, and then we can multiply again on the left by E2, and so on and so forth, all the way out to the last one, ET. Okay, and that's the proof. Any non-singular matrix is a product of these elementary matrices. So we'll come back to that in our next section on properties of the determinant. So let's go ahead and talk about the definition of the determinant a little bit. We'll start with the definition of a submatrix. Here's that definition. If A is an m by n submatrix, then the submatrix A, notation here is I vertical bar j, is the m minus 1 by n minus 1 matrix obtained by removing the ith row and jth column of A. So here's an example. Let's go ahead and look at a couple submatrices of this matrix A. First, the submatrix A23 is the matrix we obtain deleting the second row and third column of A. So we see that A submatrix 2, 3 is 1 minus 2, 9, and 3, 5 minus 1. Similar to the submatrix A3, 1, we get by deleting the third row and first column of A. Okay, so we see that A3, 1 is minus 2, 3, 9, minus 2, 0, 1. Okay, not a particularly difficult operation, but an important operation in the definition of the determinant. So here is that definition of the determinant. Suppose A is a square matrix and its determinant. The notation here is det of A, or vertical bar, A vertical bar. It's a complex number and it's defined recursively by the following. If A is a 1 by 1 matrix, then the determinant of A is just the value of A. If n is an n by n matrix, then the determinant of A is defined recursively in terms of subdeterminants of A. Okay, so we see that the determinant of A is defined in terms of the determinant of the A11 submatrix, the determinant of the A12 submatrix, and so on and so forth. Okay, one thing I'll point out here is this sort of sign floppy pattern. You get a plus, minus, plus, minus, plus, minus. And we're always multiplying by elements along the first row of A. Okay, so we'll see this first for a 2 by 2 square matrix. Okay, here's a 2 by 2 square matrix. A, B, C, D will show that the determinant of this matrix is A times D minus B times C. And we'll do this sort of carefully using the definition. Okay, so by definition, the determinant of A is the element in the first row, first column of A times the determinant of the submatrix A11 minus the element in the first row, second column of A times the determinant of the submatrix A12. Of course, those submatrices are just 1 by 1 matrices, so their determinants are just scalars. Okay, so we see pretty quickly that the determinant of the submatrix A11 is D, the determinant of the submatrix A12 is C, and the determinant of A is AD minus BC. Okay, we've seen this number before. I think you'll remember that we saw that a 2 by 2 matrix is invertible if and only if AD minus BC is not 0. So we'll see more on the relationship between the determinant of A and the inverse of A soon. So here's an example for you to check out. Go ahead and check out the determinant of this matrix. And I'll get you started, again, by the definition of the determinant. Okay, so here we see that expansion along the first row. The determinant of A is A11 times the determinant of the A11 submatrix minus A12 times the determinant of the A12 submatrix plus A13 times the determinant of the A13 submatrix. Okay, so we see that sign floppy pattern and these 2 by 2 determinants, and we can pretty quickly compute those 2 by 2 determinants and figure out what the determinant of this matrix is. So I'll let you work on that. Okay, let's talk a little bit more about computing determinants. A quick note, all of these proofs are proofs by mathematical induction. Okay, and I definitely encourage you to read these proofs, but I won't ask you to know them. They're really great, super cool proof technique, one that we haven't really talked about in this class, but is an important proof technique, the technique of mathematical induction. So here's the first one. The first one says that when A is a square matrix, the determinant of A can be computed by expanding along the ith row of A instead of the first row of A. Okay, so before we had this A11 element times the A11 submatrix, A12 times the A12 submatrix, A1n out to A1n times the A1n submatrix determinant, and here we're using the ith row of A instead. Okay, so again, the way that you show this is by mathematical induction, showing that it's true for the 2 by 2 case, and then assuming that it's true for the n by n case and proving that it's true for the n plus 1 by n plus 1 case. Okay, this can be used to show that the determinant of the transpose is the determinant of the matrix. So I won't go through that either, but it's also proved by mathematical induction. And finally, since the determinant of the transpose is the determinant of the matrix, and the columns of the transpose are just the rows of the matrix, this tells us that we can also compute the determinant expanding along the jth column instead. So here we're expanding along the jth column using those elements in the jth column and the determinant of the submatrix associated with each element in the jth column. Okay, so it turns out to be to your advantage to take advantage of zeros in computing a determinant. So I'll go ahead and let you have a look at the determinant of this matrix, and here I suggest that you first compute it expanding along the fourth row. Okay, that turns out to be sort of annoying, but it turns out to be a little bit easier to expand along the third column and we'll see why that's the case when you do that. Okay, so go ahead and check that out in the worksheet, and we can talk about it in class. Okay, we'll close with one final example. Here's an example where we're finding the determinant of a matrix T that has a special form called triangular. We've talked about this form a little bit. It's special because all of the elements below the diagonal are all zeros. Now it turns out that the determinant of a triangular matrix is always quick to find. So let's see that in this example, expanding first along this first column. So in expanding along this first column, we see that the determinant of T can be written as 2 times the determinant of a 4x4 submatrix, and then plus a bunch of zeros times some other determinants that end up not mattering because we're multiplying those by 0 anyway. To find the determinant of this 4x4 matrix, we'll expand along its first column also. So expand along this column with a bunch of zeros here. And we can leverage all the zeros in that column in order to write the determinant of this 4x4 matrix is -1 times the determinant of a 3x3 matrix plus a bunch of zeros there too. And we can play the same game again, expanding down the new first column of this 3x3 matrix, and then expanding again down the column of the remaining 2x2 matrix. And it turns out that what you get is exactly the product of those diagonal elements. Okay, in this case, again, I'm continuing to leverage all of the zeros below the diagonal. We end up with a pretty straightforward expression for the determinant that's just the product of those diagonal elements. So this always works for all triangular matrices. You can just take the product of the diagonal elements to get the determinant, and we'll see how we use this a little bit later on. All right, folks, that's it for this video on determinants. Hope you have enjoyed learning about elementary matrices, how those elementary matrices are non-singular, how to find a determinant, and then a couple extra properties that we'll see in computing determinants. And we'll see more about those properties in our next section. So long for now. We'll see you soon. Bye-bye.